Yeah, I'm Nikolai Sakharnykh. I'm a developer, technology engineer at NVIDIA. I've been with NVIDIA for about 8 years. I actually started as a graphics engineer, and then I switched over to do HPC and compute, work on HPC and compute applications. So I work with GPUs, trying to optimize developers' codes on GPUs, architectures, and trying also to enhance the architectures to get some feedback from the developers, what we need to improve in architectures and software at NVIDIA. So first of all, I guess, well, the first question is how many of you have used GPUs in your code? Can you raise your hands, please? Okay, maybe half a room, roughly, maybe more. Okay, that's good. I think last year it was actually less, fewer people, so that's good to know. Well, you know, modern systems, they have CPUs and GPUs. Like even your laptops, they need to render pixels, right? They need to draw the picture. So these are what GPUs are usually been good for. But over the past few years, GPUs have gained a significant increase, use in different HPC and enterprise and other computational domains as well, even automotive and deep learning and all this stuff. Now, usually, you would like to, utilize your system architecture as good as possible, and there are certain tasks that CPU are good for, and there are certain tasks that GPUs are good for, and these tasks are usually the compute-intensive parts of your program, where you need to do a lot of compute, or it's very compute-intensive operation. Because GPUs, they have really high throughput, floating point throughput and integer throughput. They also have very high bandwidth compared to the CPUs. So if you have some data that you operate for a long time on, and then you do a lot of computation operations, and then you're better off moving this data to this GPU and computing on it. So in general, in your code, you probably will have some sections of the code that run on the CPU that are sequential, that doesn't make any sense to move to the GPU. And there will be sections of the code that actually makes perfect sense to move to the GPU because they are compute intensive. Now, just to start with the high-level overview of the architecture, so what GPUs look like, well, they usually, a PCI Express or a device that can have its own memory, GPU DRAM. So now we also, with Pascal architecture, we support HBM as well, so high bandwidth memory. And in general, GPUs consist of multiple streaming multiprocessors. So we call them SMs. These are the core of the compute part of the GPU architecture, and they all connected to the single shared L2 cache. And then, as you go down, you have higher latencies, right? So then there goes DRAM, GPU DRAM, and then you can also, GPUs can directly access the CPU memory, host memory as well, through PCI Express or NVLink and SUDA architectures as well. And by the way, these GPUs can be also connected to, you can connect multiple GPUs together as well through NVLink, or they can sit on the same PCI root complex, for example. So in general, they can also access each other's memory as well. At the core of the compute part of the GPUs is SM. So what SM actually looks like. I have a couple slides on different SM generations going from Kepler to our recent one, which is Pascal SM. So a Kepler SM, you can see on the picture, it has so it has a lot of functional units, which we call CUDA cores, that do the actual compute stuff, right? So they do the floating point operations, they can do integer operations, they can do double precision operations. There is also a register file, and then there are different type of caches that we have on chip, right? So we have L1 cache, we have shared memory, and on Kepler, you can switch between different sizes for L1 or shared memory because they split, so you can have 16 kilobyte of L1 cache and 48 of shared memory, or the vice versa. There is also a special texture cache, and then there is a constant cache, which, and these both are read-only, right? So you only read some data, you cannot write through it. So this was on Kepler. And the register file, and then just to give you some numbers, so the CUDA cores, number of CUDA cores per SM, is about, and Kepler is 192. So this roughly tells you that you can do 192 floating point operations, single precision per clock on a SEM, right? So you can multiply this by how many SEMs you have and what's your clock rate, and you can get the peak number. Now it's actually really hard to achieve this peak number. It's, I would say, almost impossible to achieve this number. And so what we did with the next architecture with Maxwell, so we actually lowered it down. So now on Maxwell we have 128 CUDA cores. So you have, so it's easier to achieve the utilization of the SM of the compute cores that you have. And we also kept, but then we also increased the number of SMs, right? So now you have more SMs. They are easier to, to utilize. You can get good occupancy on all of them. We also increased the register file size, right? So now the overall register file size increased because you have more SMs. So per SM, the register file size is the same, but overall it's increased significantly. And the other big thing that we did with Maxwell was to merge caches, right? So previously we had a separate texture cache and separate L1 cache. Now we have a single unified cache, which is kind of a merge of the L1 and texture cache. And we also have a separate shared memory, so they're no longer sharing the same location, so they now completely separate. So you have always 64, I think, yeah, 96 kilobytes of shared memory, and you have a unified cache, and you also still have the constant cache. Now, what changed on Pascal architecture? So pretty much the SM structure kept the same. So we still have unified cache, shared memory, constant cache. What we did, we kind of tried to split the Maxwell SM into two parts, and again, trying to increase the occupancy of all these two parts, right? Because keeping your utilization of all your cores is kind of the most important thing when you're trying to run your program on the GPU. So what we did, now you have 64 CUDA cores per SM, but now we have many more SMs, so it's 56 SMs on Tesla P100. And then you have the same register file size per SM. So effectively, again, we kind of doubled the overall register file size. So it kind of doubles your occupancy. It doubles your, and also shared memory increased as well. So if you do the math, it's also, overall, the shared memory size is better. So this is just give you the overall picture of different generations of the SM, how it went from Kepler to Maxwell and to Pascal. In general, how CPUs and GPUs are different. So CPUs have large caches. They try to hide the latency. They try to minimize the latency and basically try to perform the particular sequential operation as fast as possible. And you can have multiple threads as well. You have multiple cores there. But in general, because of these large caches, you can have very nice speed for a particular certain operation. Now GPUs, they're trying to hide this latency. So all the clocks of the GPUs, they're usually lower than on the CPU, and cores themselves, they are kind of smaller. So they, you don't, if you just run a sequential program on the GPU, it would be definitely slower than on the CPU. But what we're trying to achieve with the GPUs is trying to hide the latencies to all these, memory spaces that we have on the GPU by switching between different threads. In GPUs, it's actually switching between different group of threads, which we call warps, which are 32 threads on current generation architectures. And here's a picture how it works. So you can see like a thread can do some processing. Then it for example, it's a lot, needs some data. It does load instruction. So it is waiting for the data. Then it's ready to be processed, right? So on the CPU, kind of waiting for the data regions, they're pretty small, right? So you can, most of the case, you can hit in cache. So you fetch your data pretty quickly and you move on. On the GPUs, because the latencies are so high, we're trying to switch between different warps. So for example, the first warp, it does some processing, then it starts to wait for the data. At that point, we can quickly switch to the next warp, and the next warp starts doing some work, again loading the data, and then we switch to another warp and so forth. So what happens is that when the fourth warp is completed, we can switch back. Well, when it's completed issuing the instruction, we can switch back to the first warp, and the data is already arrived there, so we can proceed immediately. So there are no gaps in the pipeline, right? So basically, we can, in this way, in this certain particular case, we can hide latency kind of completely, right? So we achieve good throughput. So this is like the main difference between the CPUs and GPUs. And from that comes the some of the key things that I want to describe how you can make your code work fast on GPUs. The first thing is, of course, since we would like to hide the latency, we really need a lot of threads running on the GPU. Try to expose as much parallelism as possible. See, because threads are slower, but we can switch quickly between them. And if you have lots of them, you can achieve high throughput. So that's the main goal. When you look at your application and trying to figure out, okay, how can I port to the GPU? First, make sure that it's really using, exposes a lot of parallelism, right? So if it's really sequential or using maybe 10 threads or 100 threads, that's not going to be enough for GPUs at all. And the second thing is, of course, GPUs and CPUs, they have their own memory spaces, right? So you would have to optimize for data locality as well. So if you know that you're going to be porting this certain function to the GPU, you need to make sure that the data is also on the GPU for this function, right? And in some cases, when you just start moving your program to the GPU, maybe only a few functions are running on the GPU. And because the rest of the code and the rest of the data is on the CPU, you kind of have to move data back and forth, and you don't gain as good performance as you would expect to. But once you port all your functions, right, or most of them, and keep most of the data on the GPU all the time, you can achieve better performance, right? Because you don't have to move the data back and forth between the steps. So try to minimize the amount of communications you do between GPU and CPU, and also between pure GPUs as well. Now, between pure GPUs and before Pascal, the only option was basically PCI Express. And with Pascal, we also announced the NVLink, which now provides much better throughputs, bandwidths for interconnect. So this kind of limitation is now, I guess, less severe than before. But you still, if you compare the HBM bandwidth, right, and the NVLink bandwidth, is still order of magnitude. Now the next thing, so once you moved your data to the GPU, now you're operating within your the memory. You don't move the data back and forth between CPU and GPU. The next thing is obviously try to move your computations closer to the chip, right? Closer to your SEMs. And this is where you would probably want to use all these resources that we have on the SM, right? So shared memory, registers, different caches, right? Read-only cache, texture cache, and so forth. And there are different ways people exploit registers, shared memory, and all the caches. But the main goal is basically trying to reduce the traffic from DRAM to L2, and then from L2 to SMs as well. If you can keep most of your data on the SMs, majority of the time, then usually you will get very, very high performance. So there are certain aspects for the memory accesses on the GPUs, and they're very important to achieve good performance. And probably some of you who already started working on the GPU and porting your applications to GPU, that you've heard about memory coalescing and how important it is to keep your all memory access to be coalesced. So what it means is that when you access your data, and the data access, they come, they've been serviced for a warp, for the whole warp, which is 32 threads. And if your warp is trying to access many cache lines, for example, and they are scattered, then your traffic will be correspondingly very, very high, and won't be, of course, high performance. the best way to deal is, right, you would like to coalesce all your data accesses so that if you look at the warp access to the data, it should be roughly, as it's shown in this picture, kind of aligned and consequent. So you have, you're fetching, one cache line or two cache lines or three cache lines, for example. In this case, it will be the best possible, performance. So trying to make sure that the, neighbor threads, they try to access neighbor data as well. So they don't go scattered in the different memory regions, because this will obviously blow out your cache and you will lose all the coalescing benefits as well. The other best practice is also to, because the GPUs, they operate, as I mentioned, on a group of threads, which we call warps. And these warps, they execute in a CMT fashion, so that each instruction, it will be executed by a group of 32 threads. And then if there is some branch condition, right? So for example, if only like 12 threads go to the first part of this branch, and then the others go to the else path, what happens is that in this first path, the rest of the threads will be basically idle, so they won't do anything. So you're wasting your computational resources, you're wasting your GPU utilization, and then only next the else path will be proceed. So the idea is that you need to try to minimize these regions, right, where you have the threads diverging and the instruction divergence. In this case, on the previous slide, it was more like a case of the memory divergence, right, when your threads try to access different memory regions. In this case, it's more like an instruction divergence. So try to minimize your divergence, in the memory and instructions as well. If you instead had a branching on a warp index instead of the thread index, this would be actually pretty good for GPUs, right? So we can switch between warps very easily, so we don't lose any performance in that case. So if you can restructure your code to make sure that you don't branch on a thread index, that would be nice. And these are just some other common best practices. I mean, basically, there's a way to synchronize different blocks. I'm not going to go into the memory, the programming model. So I'm just going to mention that there are thread blocks, right? And either you would like to synchronize, you would like to minimize the synchronization between threads in the thread block, obviously. And you can also expose more instruction level parallelism that helps usually with the performance, because you can, again, hide the latencies. There are also ways to use vector loads. You can use 64-bit or 128-bit loads. You can check that in the assembler if you're getting them or not. You can check your occupancy. You can control it with diff hints. Many different ways you can optimize your program, many different hints, tips and tricks you can do on the GPU. We have lots of resources on that, but I won't be able to cover all of them, obviously, on this talk. So I just briefly want to go over the ways you can program GPUs. Again, so mainly we have 3 different ways, and ideally your program should use all of them, or maybe 2 of them at least, at the same time. So libraries is, when you're trying to do something people already implemented, then you can just go ahead and use the libraries and APIs. And we have lots of CUDA libraries and lots of GPU libraries already written by many people. This is one of the biggest strengths probably of the GPUs, that we have really very nice ecosystem with lots of libraries. So probably something that if you're trying to port your application, this is what Peter already mentioned in the beginning. Somebody already, if you're trying to do something, probably something already, somebody already done it before. And probably there is a GPU library for that, actually. So the libraries is, kind of the drop-in acceleration, so you can just use it. Compile directive is where you can insert your, some directives and then hopefully get a portable performance across multiple architectures as well. You may not get the best performance possible, because obviously some of the special features of the GPUs, they might be, you can only program them with CUDA, for example, CUDA C. So usually the programming languages give you the best performance, kind of most flexibility. So if you want to try different things, some new features, they probably will be available in CUDA. It will take some time until they, be available in OpenACC and other standards. But compilers, compiler-X is a great way to kind of start with it, kind of looking into GPU and start porting your code to the GPUs as well. Yeah, as I mentioned, we have lots of libraries. So we have the cuBLAS, cuFFT. So these are probably standard libraries, right? And there is also recently new libraries that we announced is the MGX, QSolver, QSparse. So these are the sparse solver libraries. So QBLAS is for dense matrix applications, and the QSparse is for sparse matrix vector multiplication or sparse matrix multiplication. Then MGX and QSolver, they contain some of the solvers that you can use. So MGX has an algebraic multigrid solver with lots of different tuning options, lots of different methods you can use for the preconditioner, you can use for the solver itself, and so forth. So it's a very powerful, big library. There's also CUDA that is used for mostly, I think, for the training of the deep learning, DNN models. Then there is Courant for random number generation, Thrust, which is kind of you can think about it as a standard, STD, standard library for template library for C++. So it's kind of an alternative on the GPU. So you can have vectors there. You can have different, collectives or different functions that are kind of. And sometimes they're trying to mirror the same functionality as you have in STD, vector and so forth. And in many cases, you can actually you can pass a vector to like Thrust, and then you can do some operations to it in the same way. And it's also portable, so you can do like a host vector or device vector, and you can do the same algorithms on both. And there is also the performance primitives library, NPP. NVENC is something I haven't touched at all. And then NVBio is the library for our bioinformatics and things like string matching and things like that. So it's also, I think it's open source. So there are lots of libraries. And the new one that we announced recently is NVGraph, which is the library for data analytics and doing different graph operations. It's mostly, so right now it has the shortest path, primitive support. I think also some of the the widest path, the shortest path, and the PageRank as well. So there are like a few algorithms implemented there that you can start using, and we're adding many more algorithms in the future. So you don't have to implement them yourself. You can just use it. So for unified memory, so what it is, we have in your current systems, you may have multiple CPUs, you can have multiple GPUs. They all have different memory spaces. It's really hard to program it. So what unified memory allows you to do is it allows you to see your CPU and GPU can see the memory as kind of a single instance. So you don't have to move the data explicitly between CPU and GPU. Unified memory will do it for you. And we introduced unified memory actually a few years ago with Kepler and CUDA 6, I think at least 2 years ago. So back then on Kepler, there was some restriction that you cannot actually allocate the unified memory size larger than the GPU memory size. So it was actually limited to the GPU memory size. So it was not that usable at that point. But it still gives you a nice way to start doing some work on the GPU, because you don't really need to, when you code something, you write a CUDA function, for example, and you don't need to take care of any data movement at all. So the unified memory will take care of it. Now, this was in Kepler, and the way it worked, you can, as I said, you have to actually use a special allocator. You cannot just use malloc. But then, you can go in all your places and replace malloc with CUDA malloc managed, for example. And then you don't have to move any data at all. So you can run your kernel. You still need to synchronize, right, to make sure that the kernel completed its work and the results are written and things like that. But otherwise, you don't have to do any data management yourself. And then the way it worked on pre-Pascal architecture is, again, so when you do the CUDA malloc managed, the page is being populated on the GPU memory by default. And then if there is CPU time to touch this memory, there will be page fault. And the page will be migrated back to the CPU. And then if you run a kernel, then all the pages that you touched on the CPU will be migrated back to the GPU. We didn't have page fault support in Kepler and Maxwell. So because of that, we had to migrate all the data to the GPU once you run a kernel, right? So all the data that is touched on the CPU will have to be migrated. So it was kind of a limitation. In some cases, it actually hurts your performance quite a bit. Because if you don't touch this data on the GPU in your kernels, then you don't need to migrate it. But we cannot really guarantee that because we don't support page faults. So just to explain a little bit in this small cartoon how it worked. So first of all, when you do CUDA malloc managed, everything is allocated in the GPU memory. Then there is some thread trying to access some certain page on the CPU. There's a page fault. The data will be moved to the system memory. There's another page fault. Data will move to the system memory. And then you launch a kernel or some work on the GPU. Then we move all the pages back to the GPU memory. With CUDA 8 and Pascal, we introduced a huge update. And first of all, we added the page fault support on the GPUs. So now, and with that, we actually enabled like true unified memory. So now you can actually use the whole system memory size that you have in your system, think up to 1 terabyte. So we support 49 bits. So now you're no longer limited to the only GPU memory size. You can use the whole thing. But also, it enables you some of the things like you can actually do some optimizations on it. So we're adding some of the new features to CUDA 8 so that you can prefetch some of the data. You can also put some advices for the compiler and, for example, tell that certain memory regions will have to be reduplicated so that you're going to be using them on the CPU or on the GPU. So that please duplicate these pages on both architectures. And here's the same example, and it's completely different kind of meaning in this case. So CUDA malloc managed will work very similar to malloc in this case on Pascal. So it's actually kind of a complete replacement for malloc. So you don't actually no pages will be allocated or nothing unless you touch them on the CPU, right? And then when you touch it, there will be page fault. It will populate the pages, allocate the pages. When you touch page on the GPU, then the pages will be populated on the GPU, migrated to the GPU, and now we can also oversubscribe GPU truly so that some portions of the data might move to the GPU and stay there, and then you can still access the whole thing on the CPU, the whole memory space that you have in your system memory from the GPU. So the way it works, you have page fault. The pages are populated, right, and then allocated, and then you run a kernel. We no longer need to move all the data to the GPU. We only move pages that you're touching on the GPU. So it's moved on demand. So when you touch some page, it will be moved. Touch another page, it will be moved, and so forth. And then we might decide, OK, so page is touched back, then we move it back. If it's touched back, we might move it, or we could also establish just a direct mapping. As I mentioned in the very beginning, GPUs, they can actually access system memory directly. So in certain cases, it makes sense to just establish direct connection instead of migrating the page back and forth, because it will be trashing memory too often. So we actually detect these situations, and we map them in the GPU page tables. So this is how it works on Pascal. As I said, it enables new features like oversubscription, on-demand page faulting, right? So you only move the data that is used. It's very powerful, a new feature on Pascal and inside CUDA 8 as well. And the future thing that comes in the near future is, so we're also working with Red Hat to trying to enable the real kind of the unified system allocator so that you don't have to use CUDA malloc managed special allocator. So you can just use the malloc and then access this memory on the GPU. And then in that case, the whole thing with unified memory that I just explained for CUDA malloc, it will work the same way. So if you touch some data, the data will be migrated to the GPU. And then if you touch it back on the CPU, it will migrate it back to the CPU. Just maybe a couple slides on Summit. So Summit is a new, I think, it's the next supercomputer at Oak Ridge that will be, I think, installed in 2017. It will have the next generation of the GPU of our GPU architecture called Volta. There will be the same, HBM memory for the GPUs and DDR4. There's going to be lots of memory on this node, so 512 gigabytes. This is just to compare different, different parameters of Titan, which is the current supercomputer at Oak Ridge and Summit, which will be next. So application performance improves over 5 or 10x. Some of the other highlights might be different architectures, different interconnects as well. So we'll have NVLinks between CPU and GPU, more memory overall. So what it all means for your application, for applications that will have fewer nodes, but they will be much more powerful, right? So we'll have more very kind of large, huge nodes, and you will have to expose different levels of parallelism because you'll have CPUs, GPUs. It's important to keep them busy, to utilize your system, and likely it will require OpenMP or OpenACC programming model. And also interconnect is actually only 3x the bandwidth of Titan, and because of that, it's more likely that some of the applications will be more interconnect limited than before because of the significant increase in computational power on single node. So you'll have to exploit data locality and try to make sure that you can minimize communications between the nodes. That's all I have, and I just want to go through some of the resources. First link is the GPU, the very nice CUDA programming guide, and you can actually find there all the links to all the libraries and everything. So basically our CUDA developer zone resource center. The second link is GTC on demand. So these are our, so we usually do every year GTC conference in San Jose where there's lots of great content for GPU. And in fact, if you're trying to port a new application to the GPU, some of the first thing you should probably do is go to the GTC on demand, try to search what you're doing, for example, sparse matrices or something, or FFT or some sort of molecular dynamics, and try to find the existing people probably already presented some of the material of that at GTC. So these are GPU technology conference, so they're specifically targeting GPU, and developers present a lot of great content over the past few years. And then the parallel for all block is a nice resource. It's frequently updated, and in fact, I think I posted over the past year at least two posts there on different things. So and we, DevTech, developer technology engineers and other people, and even external people, they post on these blog posts. So there's lots of great content there as well. And the self-paced labs, these are usually, some of them are free, some of them require some credit. So you can go there and take them as well. Yeah, if you have any questions, happy to answer.
You really moved the whole thing, or just what has been changed? If you cannot answer, I will understand. I would understand.
Yeah. So
if it's a secret.
When so there, if we're talking about the unified memory, right? And there are two different versions of unified memory for Kepler architecture and for Pascal architecture. So for the Kepler architecture, we move everything to the GPU. For the Pascal architecture, we only move on a page granularity basis. So it's 4 kilobyte. We can move larger chunks as well, merged pages together. Now, we also provide a mechanism for you to explicitly move the data, which you can do with CUDA memcopy, or it's similar to memcopy, so you can just provide the source pointer, destination pointer, and how much data you would like to move. So you can move your data explicitly as well. You can move only 1 byte of the data, or you can move 100 bytes or kilobytes. Yeah.
But being more specific, you may move a memory page, right? But does not change the whole thing in the memory page, just half of it, and you have to synchronize back. You may synchronize just the difference, not the whole thing.
Yeah. So if you manage your data explicitly, then it's up to you, right? So you can, if you modify your data on the GPU, you will have to, and then you need this data on the GPU, only part of this data. You copy only part of this data, right? For unified memory, we operate on a page granularity basis. So if you modify, part of the page, we'll still have to copy the whole page to the GPU because we don't track, within the page.
You could compute a twin page before write anything and compute the difference and transfers back. that would be an alternative. Just saying.
Okay.
So Pascal onwards, you have on-demand paging and page faults on the GPU as well. Since you're oversubscribing the GPU, is there something analogous to like a virtual address scheme for the GPU as well? You can allocate more memory than the GPU supports.
Yeah, definitely. So that's what you can do with CUDA malloc managed and with even with malloc, but special request special system OS support. But you can allocate and use more than GPU memory size with Pascal.
Even pre-Pascal, I don't think.
No, pre-Pascal you cannot do this.
So from Pascal onwards, I mean, the addressing would change.
Yeah, the addressing space changed. We increased that to 40,
and
49.
then how does the page replacement strategy work out? I mean, how do I ensure that?
We're still working on that, and it's probably going to be using the list mapped, recently mapped, but then we'll see if we need to add more page replacement mechanism and algorithms there. If you have any particular example, which one you think would be beneficial, then let me know.